In this video, we're going to go over the fundamentals of the Helios context, including how it works on a basic level, as well as writing some code to demonstrate some basic functionality. The context is at the center of almost anything that you'll do in Helios. It's essentially a C++ class data structure, and it has many different member methods for working with simulation geometry and data. So its purpose is essentially to manage all the geometry and associated data that goes on within a Helios simulation. You can think of the Helios context more or less like a database. The types of data that we usually work with within a simulation are related to the geometric elements, so attributes of the geometric elements themselves, and then various data values that are associated with those geometric elements. There are two basic types of geometric elements in Helios, which we call primitives. These are either patches, which are essentially just planar rectangles, or triangles. And then from these basic primitive elements, we can put those together to make essentially any 3D geometry that we want. So the context job is to manage that geometry and its data. You can conceptually think of the context like a data table shown in this sketch here. Each row of this data table corresponds to a record, and the record is based on a primitive geometric element. So anytime we add either a patch or a triangle to the context, that's basically like a record in our database. And then each one of these records has different values associated with it. So each one is going to have this unique identifier called a UUID. This is going to be unique to any primitive within the whole context, and this is how we're going to reference it later. And each geometric element is going to have some different attributes, like the type of element that it is, its transformation matrix, color, as well as a few other things that are not listed here for brevity. So if we were to go ahead and add a triangle to the context using the add triangle method, essentially what it would do is add that to our data table, and it's going to automatically assign it a UUID or a unique identifier that we can use to reference it later. It's going to assign all of these data types. In this case, it's a triangle. It's going to create a default transformation matrix based on the version of the add triangle method that you called. It's going to assign a color vector here. In this case, it's red. We could add an image texture to color the element. Here, we didn't add one, so it's just null, and it doesn't have any data values associated with it yet. We could go ahead and add more geometry. Let's say that we wanted to add a patch that does have a texture map to it. So it would add it as a record in our context database. It's going to assign it a UUID and populate all these different attributes as well. Here we have an image associated with the texture that it's going to use to essentially carve out a star shape in this example that allows it to represent a complex pattern based on the transparency channel of a PNG image. In many cases, there may be methods within the context that can add multiple primitives at a single time in order to create an object. One example is using the load obj function to read in an obj file and create geometry based on it. So in that case, it's going to just add records for each one of those primitives that corresponds to that particular object. It's going to give each individual primitive its own UUID and assign all of the attributes as needed. Typically, the goal of a Helios simulation is to compute various values. So for example, we may want to compute the temperature field or radiated fluxes for these different primitives. Those computed or input values are stored as primitive data, and it's essentially a data field associated with each one of these records, which again is based on the individual primitive. So there's a method in the context called setPrimitiveData, So if we wanted to set some primitive data that's called temperature for primitive with a UUID of 1, then we could do it as illustrated in this example. So the first argument to this method is the UUID. We could just put it in manually, or we could, if that was stored to a variable, we could input that variable. Then we have some string that is just a label for that primitive data. In this case, we just call it temperature. And then we have the actual value that we want to set to it. So if we were to call this, it would go ahead and put that into our data table. And we can have many different primitive data values with different labels and different types associated with any given primitive. Once we've added our primitives to the context, there are many different methods within the context that allow us to either modify those primitives or to query information about them. Here are a few tables from the Helios documentation. We're not going to go through all of these individually, but some examples are applying a transformation to a primitive. Let's say that we want to translate it or move it in space. We want to rotate it or scale it. There are different methods that allow you to do that. We may want to query information about that primitive. Let's say it's surface area or its normal vector, for example. There are getter functions in order to do that. We may also want to set or change various properties about the primitive. So there are setter functions to do that, such as changing its color or changing its transformation matrix. Now, once we have our geometry and our data in our context, the idea is that the context can then be passed around to different plugins in order to either allow them to get information that they need in order to do the simulation, or to write computed data values back to the context, and then it can be passed around to different plugins. So let's say that we wanted to first run the energy balance model, so we could pass the context to the energy balance model, and then it might read some information from the context, for example, information about the geometry. It may need to know surface areas, etc. It can do its thing, do some calculations, and then write things back, such as the temperature value for each of the primitives. Once it's done that, we can then pass the context over to another model plugin, let's say the radiation model, and it can read the information that it needs in order to do its simulations. So it's going to need to know about the geometry in order to do its ray tracing calculations. It may also need to know information like the temperature, which was computed by the energy balance model if it needs to do long wave emission calculations. And then its job is to do various radiation calculations, and then it will write that back into the context that may be used by another plugin or written to file or whatever we want to do with it. If we wanted to visualize the result, we could then pass the context over to the visualizer. It can read information it needs from the context, like information about the geometry, so that it can visualize it. It may also read in, say, those fluxes that were computed by the radiation model so that it can do a visualization based on that. So here's an example of a fairly complex simulation where we've coupled all these things together, and then we've passed things to the visualizer in order to do a pseudo-color mapping of the computed radiation field based on what was computed by the radiation model. Now that we've got a basic understanding of how the context works, we're going to write a simple program in order to demonstrate some of the things that we just discussed in the previous part of the video. So I've already got open CLion here, and first thing we're going to do is create a project. So there's a previous video that goes through in pretty high detail how to set up a project in different applications. So I'll go through this pretty quickly. So we'll go into our projects folder here. I will create a new directory called teapot visualization. You can call it whatever you like. And then we'll use our project creation script in the utilities folder in order to auto-populate it. So we'll pass that the name of the directory, or more precisely, the path to that directory, and then a list of any plugins that we want it to use. The only ones we need for this are going to be the visualizer. So that should create our project here. We can expand it. We will open up our main.cpp file. We can go ahead and load this CMake project so it can start loading as we are talking. So most Helios programs start by declaring an instance of the context. So again, context is a C++ class. It starts with a capital C and then is just context. So this is the actual data type. This is similar to if you were declaring some variable as an int or a float or something. We're declaring the data type as context. And then we need to create some name for that variable. Usually we just call it lowercase context, but you can call it anything that you want. This is just the variable name. And then we add a semicolon. If we had not included this line using namespace Helios, we would get an error here, and that is because we would need to explicitly type Helios : in order to reference that the context class is part of the Helios namespace. We could also just type it for completeness if we want, but usually we just include the Helios namespace, and then we don't need to type this in front of every variable. So next we might want to add some geometry. So let's go ahead and just add a default patch. So the add patch method is a member of the context class. And good practice whenever we're working with a new method or function or something in Helios that we're unfamiliar with is to go straight to the documentation. So if we go into the user guide and using the Helios API, there's all sorts of information about the context. But there's also this searchable bar here that we can use to search for any class or method or function or anything within Helios. So we could just type add patch, search for that. There are lots of overloaded versions of the add patch function that do slightly different things. We're going to select just the default one that takes no arguments. And so we could come to the documentation. It's going to tell us that this method is a member of the context. That's what this means here. It's going to return an unsigned integer, which is the type of a UUID, which we'll talk about here in a second. And it doesn't take any arguments. And this is just a description of what it does. As I mentioned before, there are overloaded versions of the add patch method. So there's a version that takes a vec3 to define the center of the patch and a vec2 to define the size of the patch. There's a version where you can define the rotation. There are versions where you can define its color or its texture or all sorts of different things. We're just going to stick with the most basic here for now. All right, so we can call this method, and when we want to call a member method of a class, then we type the variable name that we chose for that class. In this case, we called it lowercase context. And then we type a dot, and then it's going to bring up a suggestion of all sorts of different methods that we could choose from. We're going to do add patch. So here it gives auto completions for the different overloaded versions of add patch. We're just going to call the default version and then terminate our line with a semicolon. So this just added a patch to our context. If we recall that data table, it basically assigned it a UUID. It figured out its transformation matrix, assigned it all the default properties, etc. So let's just go ahead and visualize this really quick. So as we discussed in a previous video, there are these little shortcuts. If you start with an exclamation point, there's a built-in macro called visualizer context. So this will just visualize all of the context geometry. So we can go ahead and compile and run that. We need to, as always, select our appropriate executable. In this case, we call it teapot visualization. And then we could just build it first or build and run. Let's build independently so that we can verify that everything is working. And it's just complaining that we didn't return anything from our main function. That's okay, it's just a warning, but we could put a return 0 at the end of our main function if we wanted to. And we got to the end, it says build finished. So we can go ahead and hit the play button to run it. And here we have our default patch. The default color is black. The default orientation is horizontal. It assigned it at the origin and then the default size. So there we have it. We mentioned before that this add patch method returns an unsigned integer. An unsigned integer is the type associated with UUIDs. So here we didn't actually store that UUID for anything. And what that means is that we have no way of referencing this patch later if we want to do something with it. If we wanted to, say, translate it, or we wanted to assign or get some primitive data from that primitive, we need to know what that returned UUID is so that we can reference it later. The way we usually do that is by storing the returned UUID into a variable. So we could define an unsigned integer, let's call it UUID, and assign it to this add patch call that we made earlier. There are lots of different ways that you could do this. I'm doing it all in a single line. You could define your UUID variable first and then assign it this way in 2 separate lines. This is just kind of a short way of doing it. Another thing just to highlight repeatedly is that this is the variable name. This is the type and the variable name. So I could have called this anything that I wanted to. I could call it UUID 1234. I could make up whatever name that I want. Don't get hung up by the fact that I called it UUID. It's just a variable name. That's all that it means. So now we could do something with that UUID. We could, let's say we want to change its color. So we could call context.set primitive color. And the first argument to this method is a UUID or a vector of UUIDs. So here we just have a single UUID. So our first argument, we want to pass it that UUID value. And then we need a Helios RGB color. And without going into the details, there are a number of default colors defined in Helios. So we want to type RGB : and then here's a list of all the different default colors that are available within Helios. Again, all of this is in the documentation if you want to read about it. We could also define our own custom RGB color vector to give it a different color. And let's not forget our semicolon. So if you remember before, our patch was black. Now, if we run this, we should get a visualization where our patch is now blue. And there we have it, exactly what we would expect. And now that we have this UUID, we could do all sorts of different things with it. We could, again, transform it, set and query primitive data, etc. So you may have noticed that I called the title of this project Teapot Visualization, and we haven't yet worked with any teapots. So our goal here is going to be to do a visualization of the Utah teapot, and we're going to set and visualize some primitive data in order to illustrate these different concepts. So let's go ahead and just get rid of our patch here for a moment. And we're going to instead add a 3D model of the Utah teapot. In Helios, as we've mentioned in other videos, there's this folder called PLY. It has a few different PLY models. This is just a 3D polygon file format. There are a couple of different examples. One of those is the Utah teapot model. And the Utah teapot model is a very classical 3D model. It was one of the first complex 3D model meshes that was created. It was first introduced back in 1975 by Martin Newell at my alma mater, the University of Utah. You'll still find it used today. You can find it as sort of an Easter egg in various computer graphics or computer animation applications. They'll kind of stick in this model in different TV, movies, and video games. One example is in Toy Story when Buzz is having a tea party. Then the teapot is the Utah teapot model. You can also see for yourself the original physical teapot that was used as the basis for this model. It resides in the Computer History Museum in Mountain View, California. So if we wanted to load this Utah teapot model, then here's how we would do it. We would call the context method load_ply. So for good measure, let's go back to our Helios documentation and take a look at the load_ply function. And again, we have a lot of overloaded versions that can do several different things. We'll just pick the simplest one, which is here at the top of the list. So we can see that it is a member of the context class, as denoted here. It returns a vector of unsigned integers. And these are essentially going to contain the UUIDs of all the primitives that it creates. So because the load_ply function usually loads in a geometry file that contains lots of primitive elements, it is thus going to have a lot of UUIDs, one for each primitive element that it loads. So it stores that within a vector since it can't just store it to a single UUID value. So we want to pay attention to the return type. And it's going to have a few input arguments here. The first one is going to be the path to the file, the PLY file that we want to load. And this second option is optional. And it just basically will allow us to turn off any output messages from this function if we wanted to. So if we were doing it within a script or within another function or something, we may want to just make it silent so that it doesn't tell us any output information as it's loading. And again, we have lots of overloaded versions that allow you to specify many other things to have increased control over this function or this method's behavior. So let's go ahead and call that method. So we're going to do context.load_ply. And all we're going to pass it is this very first overloaded version, which is just the path to our PLY file. And I'll repeat it as frequently as possible. When we're specifying file name paths, we either want to specify an absolute path, which is typically not desirable because if you start moving things around, then those will break. You'd like to kind of keep it within your project or relative to your project. So instead, we usually prefer to do relative file paths. But the question is, where is that relative to? And it's always relative to the directory in which you're running your executable. In this case, we're running it inside of build. That's where it put our executable file. So we need to specify our file path relative to that build directory. So that is going to be up one directory to get into our project folder, up another directory to get into this general projects folder, and then up one more directory to get into the main Helios directory. So we're going to do up 1, up 2, up 3, and then our folder is PLY, and then our file is called Utah with a capital U _ teapot with a lowercase t and then PLY. And that's all we need for the most basic version. Another thing that I'm going to do is to enable shading so that we can get a little bit of contrast within our image. So I'm going to just call visualizer.setLightingModel and then visualizer : lighting Phong to use a Phong lighting model. So let's go ahead and run that. So here is our Utah teapot model. And it's just going to be placed at the origin. It didn't rescale it or anything like that. If you get an error, most likely you either made a typo when you were typing out this text, or you didn't specify the directory correctly to where that file is located. So again, the key is relative to the build directory. Okay, so we didn't store the UUIDs from this model, so we wouldn't be able to reference those again. Let's go ahead and store those to a vector of uints. So we need to create a vector std vector, because vector is in the std, the standard library namespace. And we want a vector of unsigned integers. And we need a name for it. I'm going to call it UUIDs, plural, and then equal to. And we don't need to include the header file in order to use vectors. This is already included as part of the context.h header file, which is already included as part of the visualizer.h header file. So most of the time when you're working in Helios, you don't actually need to include any additional header files. There are quite a few that are included by default. The Helios documentation does tell you all of the header files that it includes within context.h. Those are listed here under C++ standard library include files. How did I get to this? You go to user guide and then using the Helios API and then scroll down to that part. So that would be right here. C++ standard library include files will get you down there. All right, so we stored those to a vector, and right now we're not doing anything with it. We're just storing it. So what we want to do now is to illustrate the use of primitive data. And so I want to set some primitive data associated with this teapot model, and then I'm going to use that to make a visualization based on that data, a pseudo-color mapping visualization. So what we're going to do, just for example purpose, is to assign primitive data that gives the height of each element in that model. And then we're just going to visualize based on that. So it's effectively going to give us a height ramp within our model. Not particularly useful, but it does illustrate several useful concepts. So first thing I'm going to do is to loop over each one of the primitives within our model. And I could do that by looping over each UUID value in this UUID vector. So I can use a for loop. I'm going to use a range-based for loop, which is a convenient way of looping over a vector in C++. So I'm going to loop over uint values because each UUID value corresponds to an unsigned integer. I'm going to give it a name. I'm going to call it UUID because we're just going to have a single UUID. And then we're going to loop over this vector UUIDs. So that's going to basically just loop over each one of these UUID values and then get and assign it to this variable called UUID. And then we're going to use this within our loop. So this syntax here, again, is called a range-based for loop. You could do this using a few extra lines of code using a regular C++ or C for loop. So let's just illustrate how to do that. So we could do I equals 0, I less than UUIDs dot size, I plus plus, and then we could declare some variable called UUID equals UUIDs and then index that at I. This would effectively accomplish the same thing. We just had to type a lot more. And then cline is going to tell you that's kind of a little bit more complicated than it needs to be. It's going to recommend that we use the range-based for loop instead. So it just basically rewrote that back to how we had it before. It just typed out unsigned int instead of uint as we had it before. In order to get the height of our primitive, we're going to be using a method called getPrimitiveVertices. It's a member of the context class. It takes a single input argument, which is a single UUID, and then it's going to return a vector of XYZ coordinates of the vertices of the primitive. So if it's a triangle, it's going to have 3 vertices, so we'll have an XYZ coordinate for each of the 3 triangle vertices. And if it's a patch, it's going to have 4 vertices, and so we'll have an XYZ coordinate for each vertex. So we're going to loop over each UUID, each of which corresponds to a primitive, and we're going to get the vertices for each primitive within each loop iteration. So we're going to define a vector of type vec3. So this is a vector type within Helios that's used to store 3 coordinate values, so an x, y, and a z coordinate. And then we need to give it some name. Let's call it vertices. And then we'll call this method in the context getPrimitiveVertices. And then we need to pass it a unsigned int that corresponds to a UUID. So that's going to be UUID. And that's it. Now we have all of our vertices. So then we want to just get one height value to assign to our primitive. We could take the average of the z coordinate for each vertex, but that's a little bit overkill. I'm just going to take the very first vertex and assume that that's representative of our entire primitive. Our primitives are pretty small, so that should be good enough. So I'm going to declare a variable called height. And I'm going to take our vertex vector called vertices, and I'm going to index it at the first value, at a value of 0. You could also type .front in order to get the first value. And then that's going to get me a vec3. So I think I'm going to actually do this explicitly in multiple steps. So let's instead declare a vec3 and call it vertex 0, and then we'll assign that to a variable. So now we've got a vec3. This has members x, y, and z, and so we can now declare a variable called height and set that equal to vertex 0 dot z. So you can see that a vec3 has a few different methods, it has some operators, and it has fields of x, y, and z, which are each floats. So we can do vertex 0 dot z. That's going to get me back the height of that first vertex for that primitive. Now our last step is that we want to assign some primitive data to each of these primitives corresponding to the height. So we can call the method setPrimitiveData, and our first argument is going to be a UUID. Our second argument is going to be some label that we create, a string. It could be anything that we want. It's just a label we're going to use to reference that data value later. Let's just call it height. And then the actual value that we want to set it to. So that was our variable called height. So do these need to match each other? No, not at all. This could have been height 1, in which case we just need this to be height 1. This is just a string label. This is the actual value of a variable. So now for each primitive in this model, we've set primitive data corresponding to the height value. And then we can go ahead and visualize based on a pseudo-color mapping from that variable. So let's call one more method in the visualizer. It's going to be color context primitives by data. And then we just need to give it that string that we made up for our primitive data. In this case, we call that height. And that is it. We should just be able to run it. And here we have a visualization based on height. And that is it for this particular tutorial. We learned a little bit about how the context works and how to apply it based on some code. So I hope you'll join me for the next video.